Okay, so that's our genotype and phenotype data set. So I have a couple of steps that are between now and actually doing the ridge regression. So this next step, centering predictors, is something I thought I had PowerPoint slide for. Okay, so if you've ever done a multiple regression, if you are trying to predict something with variables that are on a different scale, for example, they'll have different variance, which means it's an unfair competition between the two predictors. So if you want to know which predictor legitimately has a better explanatory power, we do what we call centering. This is mean centering usually. So that would be like your trait, you subtract the grand mean from the trait, so everything is centered on 0. We do a very similar procedure with markers to make it a fair competition between markers. And that's going to be based on the allele frequency of the marker. And so I've just provided these 3 lines of code which do exactly that. This is commonly done when you do ridge regression or when you make a marker-based relationship matrix, which we'll do a little bit later when we talk about those models. So this is just a handy script that'll calculate the mean for the markers, the marker scores, the frequency of the marker scores. You make a little matrix out of it. I'll run that and show you what it does. You can feel free to go ahead and run that too. So I guess I can kind of try to explain what this code does. I think that's a good idea. So apply is a handy function in R that'll do some function across either the rows or the columns of a matrix. So all this is doing is it's taking this matrix SNPs and it's going across. So 2 indicates the dimension of the matrix. So if you put 1, it'll do a function on each row. If you put 2, it does a function along each column. And the function is just the mean. And then we're dividing the values by 2. Okay? So when I ran this line, I guess I have to show you. So I've just kind of printed part of what it did, and it gives me, for each marker, it gives me the frequency. So minor allele frequency here is, allele frequency here is 1%, 8%, another 1%, 5%, etc. Then another row, or I'm sorry, the next line of code makes this into a matrix. And you'll see in a second what we're doing. So now we just have the same dimensions as the SNP marker matrix, and on the columns is the allele frequency of each marker. Okay? And then this final line of code makes, you'll see in the literature, this centered mark. Yes? I'm sorry? You don't have the data? Oh. Yeah. You don't have the data. I typed in this one. I want to see it in here. Getting students. So it should have run. The FREQ freak is. It's the same. It's a vector, so it doesn't actually show those. So RStudio will do the view and show you the. So the way to actually look at it is just to type in its name. Oh. That's all, and then it'll. Okay. It just prints it out. So that's what it does with a vector. A matrix will show you in that nice little form. So I think most of you guys are using RStudio, and so just a little tip, so somebody already encountered this. What we did just to look at like a matrix, like the marker matrix here, was just to kind of click on it, and it gives you this nice handy view. but it doesn't do that for a vector. So in R, if you want to look at any given object, you can just type its name in the console here. So in order to look at this vector, FREQ, you just type FREQ, enter in the console, and it'll print out the vector. You can also do that with the matrix. Either way, it's just ugly. It's not very pleasant to look at. So, so I hope that clarifies a little.
Typing head for the matrix helps.
Yeah.
But usually the first 5 lines or so, you can see this.
All the columns, and we have 1,000 columns. So another way that you can look at just a small part of it, so for example, to look at M, which is the now centered marker matrix, you use these square brackets, and then you're going to indicate how many rows and how many columns you want to look at. So if I want to look at just the first 5 rows, I'll do 1:5, and then a comma, and then I want to, let's say, look at the first 10 columns, so I do 1 to 10. And so that prints out a more friendly amount of the data set. So now you can see here. So now you'll see that the marker scores are varying around 0. So we have some negatives and some positives. And you'll see in the literature this matrix is typically called M. It's just the centered matrix. We'll do this before we make a relationship matrix also. Okay, so I'm going to move to the next step. This part is just for the purpose of being able to do some tests. So what I'm going to do here is subset. So my whole data set, everyone has a phenotype and a genotype. So what we want to do, because ultimately we want to make predictions of unphenotyped individuals, is I'm just going to pick a random set of proportion of the data, and I'm going to subset the data into one set of phenotypes and genotypes that are the training data set where their phenotypes will be observed, and the other side, the other part, the remainder will be a test data set, and we'll try to predict those individuals and see how good we do at predicting them. So all this code does is, firstly, if you run the line that starts genos here, it just creates a vector. You can print them out of the genotype IDs, the unique genotype IDs in the data set. This line here, set seed, is just meant so that when we do this next line here, sample, which is going to draw some random values, everyone's going to get the same answer in this room. So that's not necessary. You could skip this part and make your own training and test set. You'll just get slightly different answers from the rest of us, which is totally fine. So I just put that in there to make sure we could have a consistent result so that we can have things that are comparable. So you run set seed, and then you run this sample. So this sample function, what it does is it says, look at this vector genos. I can print that out if you guys want. And pick, so this just gives you the length of genos. I think it's 411, and we're going to just pick 80% of them, basically. So we're going to have a data set, 80% of the individuals will be in the training set. And then this next function is just going to make another vector that are the genotype IDs that are not in the training set. So we've just made two lists that say these are the guys that we're going to use to train the model. These are the rest of the guys, and we're going to use them to test. Okay? So you can see genos is just a vector shown here. It's just a list of the genotype IDs. This is just a slightly longer. I think it's 326 long. You can see that here. Individuals in the training set. And then 82 individuals we're going to try to predict. Okay, so why don't we take another step here, and just please call us over if you're struggling at any point here. So hopefully you're either at the same point as I'm at, or way farther ahead, which is also fine. Okay, so these next two blocks of 4 lines, all they're doing is, so first of all, we're making a new data set, phenos.trn, and this is going to be a training data set. So it's going to have just the observations that correspond to the individuals that we want in the training set. And those are the 326 individuals. We took a random sample to choose them. That's this list of genotype IDs. So if you run this first line, it takes the phenotype data set, phenos1, and picks just the individuals whose clone ID are in this list train. So use this percent in percent. By the way, there's always more than one way to do things in R. This is just my particular flavor. So this just subsets the data set. So notice we have the square brackets form here. So this is saying we want, so the which command is going to give, it's going to give a list of numbers, and those numbers correspond to the rows of this data set that have clone names that are in our training data set. Okay? And that's going to have the effect of subsetting the data set to just individuals in the training set. We then do, actually wouldn't worry about this command, just run it. This is just going to make sure everything runs fine later. It probably would even if you don't run this. So this then subsets the SNP data set that's centered, and I'm not sure we need this one, but this subsets the uncentered SNP data set. So since this phenotype data set is what's called a data frame, it's a little bit different form of object in R. It contains a mixture of character variables and numeric variables. You can't, that's why we have to use this little more complex command to subset it. So the SNP data sets are matrices. Everything in them is numbers. They don't have a column that says clone and has the genotype IDs. So the nice thing there is you can just put in the genotype IDs, and these will correspond to the row names of this matrix. So you could just put train, comma, blank, and this will subset these two data sets. You can then just run this line of code. It's doing the exact same thing and making a separate subset of SNPs and phenotypes for the test set. Does anybody have any questions about that?
All right. The big picture here is you're dividing up your data into a training set and a test set, and the rule that you're using is 4/5 for training and 1/5 for test.
Exactly. Yes. And we're only going to do this part once because now we've got the sort of backbone to do tests of different prediction models. Okay, so if we assume that that part is working, so now you're going to run this line to load the library rrblup. So this will be the first R package for prediction that we're going to use, and we're going to do ridge regression. So the first function that we're going to use in it is called mix.solve. I provided a little explanation of what we're going to do. Here, I'll just give it to you verbally as we go along. But we have one more detour to make before we can do these prediction models. I wanted to start off with this stuff because some R packages require you to make these incidence matrices. I was showing you some examples, and I can go back to them in a second. Some of the R packages you might use will do them behind the scenes, which is nice. It could be pretty convenient, but there's an element of trust involved. The R package is doing something. Hopefully it's doing the correct thing. So I feel more comfortable when I do this part. So for mix-solve, you have to make these incidence matrices. So you're going to use this model matrix command here, and this is part of the basic R. So this is built into R model.matrix. So we're going to define a matrix that is equal to, and then what you're going to do here, you put this tilde sign, and then you're going to write a formula. And these formulas are kind of pervasive in R. So if you fit linear models using the LM function, later we might use LME4, various things, you're going to write these kind of functions. And there are actually a couple of ways to do them. So what I'm doing here is I write, first of all, over here I have a part of this specifies the data set that we're making a model matrix for. And that's going to be the phenotype data set for the training data, because what this matrix is going to do is relate the observations in our training data set to, in this case, the levels of the fixed effects that we want to fit. So what I mentioned before about the data set is we've got 3 locations, and each location has 2 reps. So I consider rep nested in location. So we have location, and then plus, and then rep percent in percent location means rep nested in location. There are some other ways to specify nesting. This way makes more sense to me because it's kind of makes more sense verbally, right? Rep is in location. So I guess if we're playing with the data later, you can try different models. I don't actually have anything that's kind of like an interaction, but if you had location times year, for example, you could have location plus year plus location star, which is times year. You guys are going to have to, you can always go to Google quite easily and learn about the different ways to do these formulas in R. But this is basically all there's to it when you learn the basic formulas. Does that make at least some sense to everyone? Okay, so let's actually make this X matrix. So run that line of code, and then we can even look at it here. And that should make sense of it also. So you can see, if you look at its dimensions, it should be the same number of dimensions as the phenotypes.trn data, the training phenotype data set. It's got 1 column with all 1s for the intercept, and then it's got 0s or 1s that indicate, for example, these observations came from location B, these observations came from location C, etc. So it's just relating the data. It's going to tell the mixed solve function what model we're trying to fit. Does that make sense? Cool. Okay. Okay, so now we do the same thing for the, so let's see. So there's a little bit of a trick here that we have to do. So we make a Z matrix here that's going to correspond to, it's going to relate the phenotypic observations to the rows of the SNP data set. If you didn't have replication in your trial, you wouldn't need this, potentially, because each row, so what's going to happen here is each individual only has 1 score for each SNP, right? Only has 1 genotype. But we have multiple observations of each individual, so we're going to need to relate our phenotypic observations to the genotypes. So we make another model matrix. In this case, we just have clone. And this part is making sure that the number of levels is going to be correct. I'm not sure how to explain that one exactly, but no, clone is just a clone is the column in the phenotype data set that corresponds to the genotype ID. So it gives you the individual's identity. So we're just making a matrix that relates the observations to that. So if you look at it, well, you don't actually see any individual here, but so this would be telling, so this is going to have, this first column is going to have a 1 for every observation that corresponds to individual 1004. And then this would be a 1 everywhere where there's an observation for individual 1084, etc. Does that make sense? Yeah.
So how does the X equal function or what these model matrix functions know that all columns? Because usually you have to call, you know, the variable and the dollar sign name column. How does it know? You make a
So that's actually, you can write the model matrix that way, but that's why I have this comma data equals. I've told it the data set we're working in. So then it knows where, you know, what each name corresponds to